Hi everyone, welcome to week 5 of the Chemistry Unit 1 seminar. Today we're looking at following concepts: measurement, measurement, fuel, and the model. All of these are closely linked. And I mean, we're not really going to look at measurement, we're going to look at how to keep consistent measurements and what kind of errors that you might see. So when we're looking at any kind of measurement, it doesn't matter what it is, even the most highly calibrated machines, million-dollar machines, have a level of error. So we have a level of error. So we're looking at things like uncertainty, acceptable margins of error, so on and so forth. To the same person taking 5 measurements, even on the most calibrated machine, they're probably only going to get 4 that are exactly the same. Sometimes you'll get 1, sometimes you'll get 5, very rarely will they all be the same. I used to get worried when my experiments worked perfectly because they're not supposed to work perfectly. We do things like, to ensure we're doing things correctly, we can maintain consistency. So consistency in the way you do things. Using the same machine. There's this principle called blanking. So let's say you're trying to, I'm just going to use arbitrary numbers here. Right? So let's say you're trying to measure the amount of lead that might be in water. A lot of the time you use what's called an absorbance of light to measure how much of something there is. So let's say, again, arbitrary number, you get 0.5. Let's call it absorbance, which is this little A. We're looking at A that I'm not going to try and draw because everyone knows I can't draw. Pretend it looks like that. What we need to know is how much of that score is the water itself. So if you're trying to measure something in water using absorbance, using any kind of measurement, you need to know what the value of the water is. So let's say we're looking at lead, and the dangerous level of lead is 0.5 in this measurement. But the water that you're testing by itself actually is interfering with the test. And 0.4 of that is background interference from the water itself. Is that water actually dangerous, or is it a measurement issue? So what we do, and you can see that calibration when you calibrate any kind of machine, we set a background level of 0.4 because we know that the water by itself with nothing else in it is going to give a reading of 0.4. So we take that out of the equation. So we then have 0.1. Again, it's just an arbitrary number. But it allows us to actually say, okay, well, is this actually dangerous, or is this sample something wrong with the water that's being used? So we actually blank the machine with pure water. Often the biggest, and I don't know if you guys have heard of these, those guys that are up in senior years in uni will probably have heard of this. We're looking at significant figures. Significant figures and scientific notation. These two things allow us in our calculations to reduce the level of error. Now, we're going to be looking at the mole later. Bear with me. So the mole is that is 1 mole. Now, don't worry about too much what a mole is at the moment, but that is an obscenely big number. Now, imagine doing calculations with when you're trying to determine molarity or the mass of something involving this number. Do you think you could consistently write that without making a mistake every single time? If you can, good on you. But what we can do is use scientific notation. And you've probably seen the mole represented like this. 6 times 10 to the power of 23. So that allows us to be a lot more consistent in our calculations and avoid error. 6.0221407 something, I guess. You can remember it to its full number, that's really important. So significant figures and scientific notation are two things that allow us to reduce the level of error. When we're looking at some data that we collect in chemistry, we have two headings. We have quantitative and qualitative. Everyone has their own different definitions of what they are. Give everyone 30 seconds to think of what the difference between the two is. So, if you can hear the music in the background, I do apologize. Slide over from the so, quantitative, I always break it down like this, numbers. Things that you can quantify using numbers. Qualitative is things you describe. Example would be, okay, the turbidity of the water, turbidity being suspended particles inside, so how clear it is. Turbidity of the water went from 1.5 to 1.0. So that's a quantitative measurement. The qualitative measurement of that, or the description, would be the water appeared clearer. In chemistry, we deal with both. They call it the hard science. It's not quite as mathsy as physics, but it's not biology. But we still do quite a bit of, observing. But most of the time it's numbers, it's quantitative. Let's focus on these two for now. Significant figures of science. Very, very important if you're going to study chemistry. 9 times out of 10, the difference between the top students and, say, so the difference between a high distinction and a distinction, these two things. Because you'll be expected to answer the question to the correct number of significant figures and using scientific notation. So understanding how to do it is probably the most important part of this whole series. Scientific notation. If we have a positive, or if we have a number like 10, or we have 0.1, we represent these numbers in a different way. So 10, it's just 10 to the power of 0.1, can't see the dot there, and now is minus. So anything where you're talking about 0 point, it's a pat to the power of minus 1. If we look at 100 and 0.01, we are now at 10 to the power of 2. Because it's 2 zeros. 10 to the power of minus 2, because this has 2 zeros, one either side of the decimal point. If we jack it up a notch and we go to 1,000, 3 zeros, call it 10 to the power of 3. 0.001, shock horror, I know. It's 10 to the minus. If we go to 10,000, I think you can see where this is going. 10 to the power of 4. 0.001. 10 to the power of minus 4. Easy way to, sorry, missing a 0 there. To do this, if the number is below 1, it's 4 decimal places to the right, so it's minus 4. Here, 1, 2, 3, 4, to make 1 point, so it's 10 to the power of 4. I'm going to give some numbers now. $347. I need one more. So I want you guys to, I'm going to give everyone 1 minute. It's going to be a long one maybe. To put all of these into scientific notation. Why is this important, you may ask? Because we want to keep the margin of error as low as possible. So the less numbers you have to write, the less chance there are for errors. Okay. So 347 would be 3.47 times 10 to the power of 2. Zero 0.003 would be 1, 2, 3, 4. 3.0 times 10 to the power of minus 4. And then 1,246. 1.2 times 10 to the power. How do we know how many numbers to put down here? well, that's when significant figures come in. 60 years ago, or actually, getting to 2021, 70 odd years ago, if I recall correctly, one of the American or the European space agencies rockets exploded because all of the measurements that they were given were in metric. Pounds, feet, yards, PSI, cubic feet. So trying to then carry those into what we call the, that's the imperial system, this is the metric system, where everything is standardized against a set, of standards, I guess. So instead of everything being mixed, we have the standard international units. And all of this together helps to keep consistency throughout science. You still occasionally get some American scientists using they call freedom units. Okay, that's significant figures. I mean, that's scientific notation. So significant figures basically says which one of these numbers actually matters. So there are some rules. Again, not one of those things you really need to understand, you just need to follow them. So non-zero numbers are always significant. So if we have 1001, any zeros that are between two numbers, always significant. And what you'll notice is any zeros that are on the end of the numbers, we don't want to know about. So if we have following examples, so if we had 0.500, or let's say 632,000, they are significant. The final rule is that if we had 0.006, none of these zeros are significant, only this one. Or if we had only these two numbers would be significant. So, to sort of put it succinctly, any number that's not a zero is a significant figure. 1001, those two are between two non-zero digits, so they're always significant. Only the trailing zeros on the outside of the numbers are significant. That one is not. The numbers on the left-hand side, if they are zeros, they don't count. If this was, then all of these would be significant, but the zeros here would not be. So again, this helps to keep consistency. So if you had the following numbers in a calculation, so how many significant figures would we need to round our answer to? I give everyone a minute to do that one. So what we do is we count the significant figures. So here we have 3. Here we have 1, and we have 2. Now I hear people say this all the time. Well, how can I round that number to one significant figure? Using scientific notation. So let's say our answer here is 930. How could I round that to one significant figure? Generally, you wouldn't, but that's a good point. You wouldn't get a question like this. But you could just make that 9 times 10 to the power of 2. Effectively get rid of the 33 because we're rounding down times 9 times 2 to the power of 2. Again, probably not going to happen. All right, let's have a quick look at fuel and the different fuels that we use. Does anyone know what fuels we use to produce energy? So we burn coal, we burn natural gas. When we do all of this in a combustion reaction, now, combustion reaction is a reaction in the presence of oxygen where you have the complete breakdown of the reactants that creates a completely new set of products. Heat is then released as a byproduct, and this is where most people get confused. The heat is released as a product of reforming the bonds. So if the simplest one is methane. So you can see there, presence of oxygen, we have the complete breakdown of the reactants to form completely new products. We also get the release of heat in an exothermic reaction. So let's say we're burning our natural gas to produce energy. We end up breaking these bonds, and then these bonds reform here, and when they reform, they're releasing heat. Now, Hess's law is something we can do later. Hess, whole main world of pain itself. When we have a combustion reaction, we add heat plus methane, or whatever hydrocarbon you're burning, in the presence of oxygen. The bonds break here, they then reform, and we get heat release as an exothermic reaction. And the energy is stored in the carbon to carbon bonds of our alkanes. Now this looks nice and clean, but it's not. More radiation is released on an annual basis in 1 year from burning coal because it's filled with uranium than has ever been released by any kind of nuclear accident. Coal kills hundreds of thousands of people every single year. You get NO2 being released, you get CO2, which is a greenhouse gas, you get SO2 release, which causes acid rain, and you get, I mean, that's a small sample of it. So when we're talking about in relation to the national curriculum, the idea is that eventually we will move away from this because it's not good for us. Whether you believe in global warming or not is completely irrelevant because the byproducts of burning this stuff, not just heating up the earth, it's a whole kettle of fish. But what's released, the amount of people that are actually killed every year by us burning coal and burning fossil fuels in general is quite staggering. So I'm not going to spend much time on fuel. It's just that you understand that in the bonds, there's stored energy. We break the bonds with heat. When the bonds reform and make new products, we get a release of heat. We use that heat to produce electricity. Don't really need to know much beyond that. I think we did a fair bit of combustion reactions before we split for the holidays. Now, everybody's favorite concept of the mole. And like most things, it's not a hugely complicated idea. We know that 1 dozen is 12. So I've got a dozen eggs. Okay, I know you've got 12 eggs. Okay, I have a mole of eggs. I think this is where a lot of teachers and lecturers fail to make this distinction. But the mole is a measure of how many. How many atoms? If we look at kilogram is how much does it weigh? So these tell us two very different things. So if we look at the atomic weight of each atom, so if we look at hydrogen, hydrogen's atomic mass, no, I'm doubting myself if it's 1.008. Yeah, 1.008. One 0.008 grams per mole. Another way to put that, in every 1.008 grams of hydrogen, there is that many atoms. So the biggest struggle I see is with a topic called stoichiometry or stoichiometry. which makes us transfer from grams to moles. And we're going to do that. Again, to sort of recap, the mole is a measure of how many. So if we say I've got a mole of eggs, or a dozen of eggs, they just mean a set number. Kilogram refers to how much does something weigh. And we can chop and change between them using what we call the atomic mass unit, which is found on the periodic table. But you'll get to an exam or an assignment question and it'll say, what is the mass of hydrogen if I have 16 moles? And it's a really simple bit of maths that we're going to do. So we're going to look at hydrogen and nitrogen. So hydrogen, (1.008). Nitrogen, atomic mass unit of 14.01. Remember the units, grams per mole. So you can determine by this number that nitrogen is about 13.5 times heavier than hydrogen. So let's say I say to you, I have 84,000 grams of nitrogen. I also have 24,000 grams of H2. But I want to mix these together and see which one runs out first. When I ask this question, I say, which of these two has the most atoms? We know that nitrogen has the biggest mass, but we know the mass or kilo or weight, depending on what you call it, doesn't tell us the most number of atoms. So what we need to know is this number here. So we can use this to calculate the number of atoms from the weight or the mass. Does that sound like fun? So if we, let's do nitrogen first. So I want to know how many moles of nitrogen. I want everyone to take a minute and think. So we can use some tricky maths. So we start with 84,000 grams. So 84,000 grams, we have 14.01 grams per mole. And how many, if we've got N2, we have to times it by 2. Because there's 2 of them. And we divide 84,000. And in doing so, we get rid of the grams. So that will give us 3,000 moles. Now, let's look at hydrogen. There's only 24,000 grams. The AMU of hydrogen is so again, we're getting rid of the grams. Anyone got their calculator and want to do that? So yeah, James, you would be correct. $11,900 moles. So this is why we don't rely on mass. We have to use the mole. There's some other concepts with the mole. Things like molarity. So does that make sense about the mole? It's a measure of how many, not how much something weighs. So we've got, so molarity is essentially how strong something is. So if I take 1 scoop of Milo and I mix it into 100 mils of milk, or I take 1 scoop of Milo and I mix it into 1 liter of milk. You're going to get 2 very different solutions, aren't you? So if you take, and this is why molarity is important. If I took 100 grams of hydrochloric acid and I mix it into 10 mils of water, it would burn my skin off and go straight through my body. If I put 100 grams into 5,000 mils, I mean, it'll still be pretty strong, but it's not going to melt my skin off if I get too close. Well, if I mix 1 mole of hydrochloric acid, the molarity is going to be significantly different. . So molarity is effectively just a measure of concentration. And it's really important to get right. Right, I think I'll leave that there. That's a lot of information to go. I'll get these recordings up and send them out to everybody. And I will see all you guys in the week or next week. Have a fantastic week.